We're going to be talking about all the colligative properties. So far we've discussed the lab that relates to freezing point depression, but we're going to add 3 other colligative properties to that. So colligative properties can be defined as properties that depend on the number of solute particles dissolved in solution. And to be more technical, it's really related to the ratio of solute particles to solvent particles. We're not going to use that technical a definition. What really matters is that any solute that dissociates into multiple particles, each of those particles will affect these colligative properties. So there's a list. We've talked about boiling point elevation and freezing point depression already, but we will discuss those a little bit more in detail now. Also, vapor pressure lowering. The vapor pressure lowering is actually the reason why boiling point elevation occurs, and we'll talk about how they're related. And then osmotic pressure, we're going to finish with that. And this is something that you may already be a little bit familiar with from biology courses, but we're going to talk about that a little bit as well. Boiling point elevation and freezing point depression. This is the equation for boiling point elevation. Delta TB is the increase in boiling point. I is an integer called the Van't Hoff factor. It's usually an integer, at least in this class it will be. We'll talk more about that in a minute. Kb is the boiling point elevation constant, and lowercase m, of course, is molality. We talked about that earlier in the chapter. This is the equation for freezing point depression. It should look very, very similar with the exception of the F subscripts rather than the B subscripts. Delta Tf is the decrease in freezing point from the freezing point of the pure solvent. I is the same Van't Hoff factor we talked about a little bit already, but we'll talk more about in a minute. Kf is the freezing point depression constant, which is a constant for a given solvent, and it will be different than the boiling point elevation constant. Those numbers would be provided if you needed them. And m is still the molality. So let's talk about the Van't Hoff factor first of all. We've already seen this a little bit when we looked at the freezing point of sodium chloride solutions and compared those to the freezing point of non-electrolyte solutions like ethanol and methanol. And we noticed that sodium chloride, because it dissociates into 2 particles per solute particle, that it has an exacerbated freezing point depression, that it has more of an effect. So the Van't Hoff factor is defined in your book as the moles of solute particles divided by the moles of intact solute before they dissociate. So let's make sure everybody knows what that means. First of all, this is a table, and we're going to talk about this table a little bit more now. Here is our table with our expected Van't Hoff factor, which is abbreviated with an I, and that's the first thing I want to talk about. So we're going to put that up here, and I want to talk about each of these electrolytes. So I'll start with sodium chloride solid, which when we dissolve it in water is going to form a sodium and a chloride ion. And that means that it forms 2 ions per formula unit, which means it has 2 moles of ions per mole of solute. So we have 1 mole of intact solute, 2 moles of particles, quote particles, which is our generic word for ions, which means our Van't Hoff factor is 2, right? 2 moles of particles divided by 1 mole of intact solute. Now let's talk about magnesium chloride. We've already talked about this a little bit. We have 1 magnesium and 2 chlorides, which means we have 3 moles of particles on the right, which means I is 3. Magnesium sulfate. Don't get confused by sulfate. Sulfate is a polyatomic ion, so it stays intact, SO4 2-. So I is 2, just like it was for sodium chloride. Last but not least, iron 3 chloride dissociates into an iron plus 3 and 3 chloride ions, which means it has 4 particles on the right and 1 particle on the left, which means I is 4. Now the last thing I want to talk about when it comes to this Van't Hoff factor is the observed Van't Hoff factor. This is less important than the other things we just talked about, okay? It's important that you guys can do the things I just did, where sodium chloride dissociates into 2 moles of particles, therefore I is 2. You will need to know what I is for each of the ionic compounds that I might give you. Now this last little tidbit of information is not quite as important. It's just to let you know that this table exists because the expected Van Hoff factor that I circled in red is not always what we observe. And I just wanted to briefly explain why that is. That's due to a phenomenon called ion pairing. And you've already learned a little bit about why that might happen, but let's look at a beaker, and we have sodium chloride dissolved in our beaker. And we have these two ions. We have cations and anions. Our water's gray today, apparently. And in this case, it looks like our ions have separated. The particles are all separated from each other. However, you know, cations and anions are very attracted to each other. And so if we have them in a sufficiently concentrated solution, and you can see those little dashed lines are like intermolecular forces, right? If they're attracted to each other, then they may be attracted to each other even in solution. So in this case, I'm putting this green box around it because in this case, this is meant to show you that this pair of ions acts as a pair. It acts as one unit. And so sometimes when we have these oppositely charged ions, they're so attracted to each other that they behave as one unit and not two because they pair together. And so you end up getting some value between the maximum expected theoretical value for I, and you end up getting a slightly smaller value. And that's why. So they sometimes behave as one, not two, and so you get a number between the two. Okay, so the take-home message from the Van Hoff factor is that sometimes the Van Hoff factor is not what we would expect due to ion pairing in solution. That's the I observed. But the I expected, those are the things that we're going to use in our calculations, and you will need to just know what I is based on the formula of the electrolyte. So for example, you'll need to know if I give you a sodium chloride solution that I is 2, and if I give you magnesium chloride, you'll need to know that I is 3. So you should practice those, make sure that you know what integer you'd use for those calculations. This is a table of boiling point elevation and freezing point depression constants for different solvents. You would have these available to you if you needed to do some calculations involving them. Notice that the units are degrees Celsius kilogram per mole. That's because delta T is going to be in degrees Celsius, and of course molality is moles per kilogram, and so that's why moles and kilograms are also in those units. Those should cancel out to give you the correct units when you do the calculation. We'll do some examples in a minute. Now let's talk about why this occurs. Why is the boiling point elevated? Why is the freezing point depressed? And before we talk about that, we need to first talk about vapor pressure lowering, because vapor pressure lowering is the reason why boiling point is elevated and freezing point is depressed. And so we need to talk about that first. Vapor pressure lowering is on our list of colligative properties, so that's going to be the next one we talk about. And then we'll come back to boiling point and discuss why vapor pressure affects boiling point. So here is a beaker, and we've tried to close it off there with a watch glass. Obviously that doesn't work super well, but let's pretend it closes it off. And we're going to have just solvent alone on the left, and we have solvent and solute on the right, and this is a non-volatile solute, so it's going to stay in the liquid phase or in the aqueous phase or whatever at the bottom. The solute is the red particles, and if you think about the solvent, as the solvent evaporates, it evaporates from the surface. And the solute particles, the more that are present, the more they sort of get in the way of the solvent at the surface escaping into the vapor phase. And so the more solute particles we have, the more they will impede the vaporization of solvent, because they just physically get in the way of those particles being at the surface. So the vapor pressure is lowered whenever you have a solute dissolved in the solution. This is the equation for vapor pressure lowering. This P vape on the left is the vapor pressure of the solution. Chi there, we've already learned that earlier in this chapter. That's the mole fraction of the solvent, in this case not the solute. And then P vape with the little circle up there, that's the vapor pressure of the pure solvent. Okay, so you would use that equation if you wanted to calculate the vapor pressure of a solution. Now let's talk about why vapor pressure affects boiling point. So if you remember, this is a picture we looked at before where we tried to talk about what boiling was. Okay, so remember that in the case of something boiling, what happens is we're raising the temperature and the vapor pressure starts to go up, and eventually the vapor pressure will equal the atmospheric pressure. And at that point the bubbles can form because they will not be crushed by the atmosphere. So keep in mind that we have lowered the vapor pressure by adding a solute, right? Vapor pressure lowering in a solution. And what that means is that if we take that same solution with the same solute dissolved, if it has a lower vapor pressure at any given temperature, then that means it needs to reach a higher temperature in order to reach the atmospheric pressure. And so we have to raise it to an even higher temperature to get it to boil, which is why the boiling point is elevated. Look at a phase diagram. So phase diagrams are something we introduced in the last chapter. The blue line is just the line that separates the solid and the gas, but the red line is the line that separates a pure liquid from its solid phase and a pure liquid from its vapor phase. The green line, however, is what you would see for a solution, and so the boiling point is elevated. And so if you look at the 1 atmosphere line on the pressure side on the y-axis, and that goes across all the way, then of course boiling is the line that separates the liquid and the gas. And you can see that the boiling point needs to be higher for the solution, right? That's the delta TB that you see. And you see a similar delta TF as well. Those are also relevant to the 1 atmosphere vapor pressure. The final colligative property is osmotic pressure, and this is something that you're already probably a little bit familiar with, whether you know it or not. This is the equation for osmotic pressure. The uppercase pi is the symbol for osmotic pressure. That's here, and then molarity, and the ideal gas constant is R, and T is temperature. Now this picture here is trying to depict what osmotic pressure is, and so we have a semi-permeable membrane, and we have a blown up version of that at the bottom in the little circle, and you can see the little dashed line is our semi-permeable membrane. Semi-permeable means that solvent can get past the membrane, but the solute cannot. The solvent particles are shown in little blue spheres, and the solute, which can't go past the membrane, is shown in green. So in this particular cartoon, the solution is on the right, and so the solution has solute particles dissolved in the solvent, and on the left is just pure solvent. You can see that also in an expanded molecule glasses view at the bottom. Now if we think about what's going to happen here, of course we have a lot more solvent on the left than we do on the right because the solute particles take up some of that space. So the solvent particles, the blue ones, are going to want to move to the right because they have too much concentration on the left, there's a lower concentration on the right, so they want to move to the right, which is why there are 3 arrows moving to the right and only 1 arrow moving to the left. So the net movement of solvent goes to the right. So what happens is that the level of liquid on the right will increase. So if we see that, you see that the level on the right, the green side, is higher. Now eventually what's going to happen is that column of liquid is going to exert pressure, and that is going to eventually counter the flow of solvent across the semi-permeable membrane because the pressure will get too great for it to increase in level any higher. So the difference in the height of those liquids, the pressure that exerts will eventually stop the flow of liquid. So once the flow stops, you measure the height of that column and the pressure that it exerts. That is the osmotic pressure of that solution. Another way to think about osmotic pressure, if we use the same diagram on the left, and instead of allowing the solvent to flow, if we actually exert pressure on the right-hand column, and the amount of pressure required to prevent flow, to exactly prevent flow of solvent, that would also equal the osmotic pressure. So those 2 pi numbers on those arrows, those are identical. That would just be 2 different ways of measuring the same osmotic pressure. Now, osmotic pressure is related to cells because, of course, cells have semi-permeable membranes, and cells are dramatically affected by osmosis. Okay, osmosis is the reason why plants have cell walls, because if they didn't, they would shrink. The change in osmotic pressure would be too great and they couldn't maintain their shape. So the picture on the left is a picture of a cell, that's the gray, and the cell has been placed in a hypertonic solution where the solute concentration is high on the outside. So when a cell is placed in a concentrated solution where there's more solute in the solution than there is inside the cell, what happens is the water will want to flow out of the cell, just like it wanted to flow in the previous picture with the osmotic pressure cartoon. So if the water leaves the cell, it results in something called crenation, which you may have learned in biology, and the cell shrinks. However, on the right-hand side is a cell that has been placed in a hypotonic solution, and so in that case, hypo means below, and that has a lower solute concentration than the concentration in the cell. And in that case, water will want to flow into the cell, and that will eventually cause the cell to burst, and that is called lysis. Now the other term here, of course, other than hyper and hypotonic, would be isotonic. Iso means same. Isotonic solutions have the same concentration of solute as the cell cytoplasm. And so they don't crenate or lyse. They just are. So it's important when you work with cells that you use isotonic solutions unless you want the cells to break, which you don't usually, but sometimes you do.